Hello guys, I'm Anmol Panda from the Programming Club of IIT Madras. So today we'll be discussing the solutions of Google Kickstart Round E. So yeah, let's get started. I was able to solve problems A, B, and C. I'll be discussing the solutions to problems A and B now. And in the latter part of the video, one of my friends, Chahel Singh, will be discussing the solution to problem C. So yeah, let's get started with problem A. So problem A, coloring game. So I'll explain the problem first. What it says is that a game is being played. There are n cells in the game. So, simultaneously we can draw a diagram. Okay, so there are n cells in this game. Now, all the cells are initially colored white. A cell is valid if it has white color and it does not have any adjacent red colored cell. Okay, so initially everything is white out here. And what happens is on each turn, a player paints a valid cell with a red color. So suppose say the player 1 painted this as red color. So player 2 cannot paint this one as red color again because this thing is already red in color. This thing is already red in color, so player 2 cannot paint this one as red in color. Okay, so that is the first part of the problem, and there are two players in the game. One is John and one is Bot. So John has played the game a lot and the bot is poorly trained. So he paints the first valid cell from left always. So both of them play, John plays optimally and the bot plays according to this rule that it always paints the first valid cell. So you're supposed to find the maximum achievable score by the bot, and this is assuming that John is playing optimally. So one thing is very obvious, like initially everything is white. So the first valid cell and the numbering starts from here. So this is 1, this is 2, this is 3 and so on. So the first valid cell is this one. So what he does is the bot comes and paints this one red. Now the aim of John is to minimize the number of reds which the bot has got. So John has choices from here to the end of the array. He cannot paint it here because two reds cannot come adjacently. So suppose John paints here. His aim of this thing is that now the bot also cannot paint here. The bot cannot paint here. And the bot cannot paint here too. So the bot has to paint the next color to be here. So here we see that in the first 5 boxes, or and this procedure would repeat again and again. So again, if we have more boxes out here, so again John would want to paint his blue here and so on. So this is one approach for John. In this case, what happens is observe that this pattern of red cross is denoting the bot's move, and the blue cross is denoting the John's move. So this pattern is repeating again and again. So every 4 moves, the bot has one move to play. So the bot score will be roughly around n by 4 in this case. Okay, roughly around, like if it's n is not divisible by 4, he can make another move. To be very clear, it'll be seal of n by 4. But yeah, it'll be close to n by 4. So this is one approach which John can play. Now, are there other approaches? Can John do something else to minimize the score? Okay, so we can come back to the original condition again. So the bot moved here. Now we have checked about this position. What happens? If this is the case, then we know the answer is n by 4. Now let us consider that John makes his move out here. Is this better than the previous case or not? Observe one thing here. When John was making his move out here, he was preventing the bot to move from positions this one and this one. These both are the positions which John restricted the bot to move. So he cannot move in this position and this position. So there are two positions which John is restricting the bot to move. Now suppose John makes his move in this square, Now how many positions is John restricting the bot to move? The bot cannot move here because there's already a red cross out here. The bot cannot move here, so there's already a red cross out here because there is a red cross here. Similarly with this also. So here John is stopping the bot from moving from three places. Suppose there are more boxes after this. So the bot can make its next move out here. And then John can continue this process again and again. So observe that in this case is better than the previous case, is my claim. Now why I'm claiming this is that the bot needs to make less number of moves. So there have to be more number of squares where the bot cannot make moves. So here you see, when John makes a move, he's stopping the bot from moving into these three positions. The bot cannot make a move in these three positions. It's got slightly clumsy. I'll probably clear the board slightly. Yeah. So the bot cannot make a move in these three positions. Earlier what was happening? Since John was only moving here, the bot was not able to make a move in these both positions. Sorry, in this position. The blue correspond to the first case and the black correspond to the new case. So in the second case, the bot is not able to make a move for more number of positions, which means his number of moves also will be lesser. Now in this case, we can do a analysis of how many moves he does also. So now this thing will actually repeat again and again. What would happen is, suppose there are 5 more blocks out here. So the bot will make its next move out here because this is the first valid square. This is not valid, this is not valid, this also not valid. Now John can do the same thing again, to minimize the number of moves of the bot. You maximize the places where bot cannot make a move. So John makes his move here again and the same procedure continues again and again. So observe that here, this thing is repeating. In 5 boxes, the bot is able to make one move. So every 5 boxes, the bot is able to make one move. So in n boxes, he'll be able to make roughly around n by 5 moves. The actual answer would be seal of n by 5, but we would do the exact move analysis in some time. So yeah, this, and we need to minimize the number of moves. Sorry, John plays optimally to minimize the score of the opponent. So John would obviously want to play in this way so that the bot has lesser moves. And in this case, the bot is guaranteed to have these many number of moves. So this is the maximum possible score the bot can get. Now, another question comes. Can John play more optimally than this? The answer is no. Well, let's see how that happens. So we have seen that, just a minute, yeah. So we have seen that if John makes a move here, it's n by 5. So let's see what happens if John makes a move here. Now this is actually not a very optimal way to play. The reason is that it's not like he's preventing the bot to make a move in all the 3 moves. The bot can always make a move out here because this is a valid square now. You see that this is empty. This place is empty. This place is empty. So this is a valid square because it's not surrounded by any of the crosses. So the bot can make a move out here. Now you see what was happening, like initially we were leaving a gap of 3 in every 5 squares. Three spaces were being vacant. Now you see only 2 spaces are being vacant and the bot has also made two moves out here. So say John continues this thing again. Now say John wants to make any move out here. Whatever he plays ahead, whatever he plays ahead, like whatever the sequence might be, this case is always more optimal than this case. The reason is that in this case, the first five blocks had only one move by the bot. And then this part, the right part, is remaining the same for both of them. So even if the number of moves are same in both these cases, the first block has lesser number of moves in this case. So this is more better than the case where John is making the move in the fifth square. So overall, this is the most optimal case. Now we can see the number of moves in this case also. So I would just like to clear the screen a little bit. So yeah, so now we know John has to make his move here for optimality. Now what will happen after this? Now what is the first valid position? The first valid position is this one for the bot. This one. And then John does the same thing again and again. So we know this part repeats. So in every five things, the bot makes one move. So if it's n things, it will make n by 5 moves. So given n is divisible by 5, you're able to make this unit exactly an integer number of times. So suppose n is a multiple of 5, he can make exactly n by 5 moves. So that is one case. The second case is n is not a multiple of 5. Now suppose n is not a multiple of 5. So what you do is you consider the number n minus n mod 5. This is basically the highest multiple of 5, closest to n. Sorry, less than or equal to n. So in this case, it's again the similar case as this one. So this is a multiple of 5. So the bot can make these many moves divided by 5. Now there are also few squares left, which is non-zero. There are also few squares left out here, which are non-zero. And observe that after every block, the first block is being a valid square. After this block of 5 moves, after this block of 5 moves, the first block is being valid. So after these many blocks of 5 moves, there are some blocks still left. And what will happen here is the first block will be a valid move. Always. And this first block will always exist because this is a non-zero number. So the bot can make one extra move and only one extra move because this is lesser than 5. So John will make a move so that the bot cannot make any more moves. So this would be the case if n is not a multiple of 5. Now while we do integer division, so these are the two cases. While we do integer division, n modulo 5 will be a number less than 5. So n modulo 5 by 5 will be actually 0 because we are doing integer division out here. So this would be n by 5 plus 1. Suppose n modulo 5 is not equal to 0. And if n modulo 5 is equal to 0, this will be exactly n by 5. So yeah, that's it for the problem. And I've written the code also for this. So k is equal to n by 5. Now I'm subtracting 5 into n by 5. Now this will basically check whether if n is a multiple of 5, n will become 0 after this move. I could have written n modulo 5 equal 0. That is also another thing. This is also fine. So n by 5 moves in either case. And suppose n is not a multiple of 5, that is n is not equal to 0 after doing this operation, then I increment k by 1 and I print k for this. So this was a pretty straightforward problem. Now just a piece of advice. In problems usually like say problem A or problem B, now a greedy problem like something like this, it's better not to see the sample cases initially before giving an attempt to the problem. Because you see, the sample cases, it has been discussed that John is making his move out here, which is actually not the optimal case. But in case of n equals 6, this gives the right answer either way. And I'm sure many of you might, directly have seen the sample and, outputted something like n by 4. The case we took initially where, John is making his move out here. So that is not actually the optimal case. Initial greedy problems, what happens is the problem setter makes a sample cases such that, they can be explained in some other method, but that might actually not be the method to the original question. So yeah, that's just a side note to this problem. So yeah, this was problem A, and let's move on to problem B. Now problem B, what it states is that we have n students. So I'll just clear everything. Yeah. So we have n students. Now each student has a rating Ri. Okay. So we have been basically given an array of students. So each student, it's a rating of n integers, and everything is Ri. Sorry, the ith element of the array is Ri, where Ri is the rating of the student I. Now what is supposed to be done is each student wants a mentor to help him in his preparation. So what the mentor will also be in this array itself. There's no separate array given. So a student can be a mentor to another student. And also each student will have exactly one mentor, but one mentor can be a mentor to many people. A person can be a mentor to many people. Now also another condition is given that suppose the mentor you're picking is RJ, jth student is the mentor, then this condition has to be imposed that Rj, the rating of the mentor, should be less than equal to 2 into Ri. And the student also wants the strongest possible mentor. Basically, wants the highest Ri as the mentor under this condition. So, we want the highest Rj in the array, which is less than 2 into Ri. So, we want the highest element in the array, which is less than 2 into A of I. Okay, I'll repeat my thing again. We want the highest element in the array which is less than equal to some number. Now, the reason I repeated this thing twice or thrice, when I speak this thing, the first thing which should come in your mind is something like a lower bound or an upper bound in an array. So, for people who are not familiar with lower bound and upper bound, so just I'll give a brief description. So what lower bound and upper bound does is, suppose you have an array, say something like, I'll take some values, 1, 4, 6, 9, 10, 12. The array has to be sorted. That is one important condition. So suppose you have an array and I say upper bound of, I'll write it UB in short, upper bound of 7. What this will do is, this will retain an iterator or a pointer to the first element in the array which is greater than 7. In this case, it is 9. Now lower bound of 7 will return the first element in the array which is greater than equal to 7. The core difference here is equal to. Lower bound checks for equality also. Now here the condition is same for both, because 9 will be the answer for both of them. I'll not return 9. Suppose this is an array whose initial pointer is A, then this would return A plus 3. Okay, so upper bound and lower bound would return that. But suppose we do something like upper bound of 6. Now it goes from the beginning, it returns the first element which is greater than 6. That is 9 out here. Okay, so upper bound would return this thing. But if I do lower bound of 6, it would return the first element that is greater than equal to 6. Because 6 itself exists. This is the answer out here. Okay, so that is basically what upper bound and lower bound does. Now, yeah, but how do we apply upper bound and lower bound out here? Now, what is given out here is, suppose this is my array itself. Just a minute, I'll just erase this thing. Yeah, suppose this is my array of ratings in sorted order. Now, this initial rating array is not given in sorted order. So I sort the ratings. Now for every element, I want to find, 2 into Ri. The bound is 2 into Ri. So like some of you might be having a question, since we are sorting the elements, aren't we disturbing the order of the elements? So the new ith element might not be the old ith element. That is true. So what we could do is, the initial array, we could, store this in some temporary array. Say the initial array is a1 a. We could store this in something like a1 of n, and we could sort the initial array. So in this way, we also have track of the elements as they appeared initially in a1 of n, and also we have the sorted array and different array. Okay, so that's something where you can retain the ith element also by using another array. So now you want to find the highest element less than 2 into Ri. Okay, so what I am saying is, what we can do here is that we find upper bound of 2 into Ri. Okay, now what this thing will do is that in this array, this will give the first element which is greater than, okay, which is greater than, which will give greater than 2 into Ri. Now we want an element which is less than 2 into Ri. So suppose this is the element which we are getting by the upper bound. I'll just go one element back. Now it is guaranteed that this element which you have found is less than 2 into Ri. Why? Less than or equal to 2 into Ri. This less than or equal to. Why? Because upper bound is returning the first element. It's returning the first element which is greater than. So if I go 1 minus, it'll return the last element which is less than or equal to. Okay, and that is what we actually want in our question also. We want the last element. Last in this case would be the strongest, would be the element with the highest rating. The reason is that we have sorted the array. So since we have sorted the array, we would get the higher elements would be this side and the lower elements would be at the beginning. So if we do upper bound minus 1, we would get a desired output. Okay, so this is how we would obtain the mentor for a given student. Now, when can a mentor not exist for a student? Okay, so we'll just clear out the board. Yeah, so we can just take one of the examples out here itself. Say something like 2500 and 1200. Okay, so 2500 and 1200. Now, one thing is that suppose for 1200, now this is my A1. Now my A is actually, I'll sort these elements, so it'll become 1200 and 2500. Now I want to find, suppose I want to find the mentor for, the 1200 one. The person with the rating 1200, I want to find a mentor for him. Now what I will do is, I will do upper bound of 2 into 1200. That is what we have discussed. First we'll do upper bound of 2 into A of I, and then we'll subtract 1 to get our original thing. So, what we do is upper bound of 2 into 1200. Okay. We get, that is upper bound of 2400, right? So basically we want the first element greater than 2400, that is 2500. So this is our upper bound. Now what we have already discussed, we want upper bound minus 1. So upper bound minus 1 will point to this element. So this guy can be a mentor. But observe that this guy is only the student. So this is the mentor and this is the student, which is a contradiction. The same person cannot be a mentor and student for the same guy. Like A cannot mentor his own self is the basic thing. So we are getting the after this upper bound thing, we are getting the same person as the mentor. So this case is actually not possible. Now suppose in this array itself, suppose there was say another element out here, something like 900. Now by doing the upper bound thing, upper bound minus 1, we have got that our answer should be this. But we know this is not possible because he's the initial student itself, so he cannot be the same mentor. What you do is we go one step back. Do there exist elements in the array? One step back. There exist elements. In this case, there exist elements, that is somebody of 900 rated. Now this guy can be a mentor for this. Also just I forgot to mention. You can the mentor can have a rating lower than equal to mentee's rating. So it's not like somebody of 900 rated cannot be a mentor of 1200 rated. That might seem against the general common sense, but that is what the question is given. So here the 900 guy can be a mentor to the 1200 guy. But in the case they have given out here, there is nothing before 1200. So there are no more elements. So for 1200, there cannot exist a mentor. So as a gist of the problem, given an array, what you do is you do upper bound of 2 into a of I. So suppose you get something here. Now what you do is you go one step back. Okay, you go one step back. Now this is a probable solution for us. So what you check is the person one step back, is his rating equal to the initial rating or not? Okay, so because if his rating is equal to the initial rating, then that guy can be the original student. Okay, so if that is the case, he cannot be the mentor. So you check whether elements are existing behind or not. Suppose there exists an element behind, there exists an element behind. You output this as mentor. Okay, now just a doubt which might be coming in some person's minds, some people's minds, that suppose this guy is 1200 rated, this guy is also 1200 rated. Now what would happen here is you do the upper bound thing and you arrive at suppose this point. Now this actually might not be, suppose we are considering this for a of 2. Okay. Now what might actually happen is this might be a of 2 and this might be a of 3. But it's still fine because the only factor given here is rating. So by rating, you cannot actually distinguish between a of 2 and a of 3. So even if this is the case, you could always assume that this is a of 2 and this is your a of 3. Okay, so if you are say manually sorting in such a way, some way, and not using the inbuilt sort, so what might happen is this might be the second element for you, and this might be, sorry, this might be the second element and this might be the third element. But it's always safe to assume, safe to swap these both elements also, because they have the same rating, and the only thing which is distinguishing people here is rating. So that is also not going to be an issue if there are duplicates in the array. This approach would work nevertheless, whatever the situation is. Okay, so yeah, that's it for the problem, and I've written the code out here. The thing is small out here, so I would just probably copy paste it somewhere, say in a notepad. So yeah, this is my void solve function. So what I do is I initialize the vector, I take input. Now I store the vector in another temporary vector, as we initially discussed that we need to maintain an order of the elements, because we are taking care of Ri and Rj. So after you sort, the ith element of the old thing might not be the ith element of the new thing. So store them in some temporary thing. We sort the initial vector out here and we do upper bound 2 into v1 of I minus v dot begin. Basically this retains an iterator from v dot begin. So minus v dot begin I do to get the position. Now we have also decided that we need to do it minus minus. Basically, we are going to the element just before the thing. We have discussed out here. Suppose our lower bound is giving this. We're supposed to go just one element behind. So yeah, so that is the thing. We go behind. Now suppose v of it is equal to v1 of I. That is, we have taken the case where the mentor can be the student itself. We subtract it minus minus. Now if it is equal to minus 1, basically there are no more elements existing anymore. If it was some positive value, it would point to some element in the vector. But if it is minus 1, basically it's pointing to no other element. I print minus 1, or else if there exists element, I output v of it. So yeah, that's it for problem B also. Now, problem B also was a fairly easy problem, a standardish problem. If you knew upper bound and lower bound, then it was a decently easy problem. So yeah, that's it from my side for the editorial. Now, problem C also will be discussed in the latter part by my friend Chahel Singh. Uh, if you have any queries regarding any of the two prompts I have discussed, so feel free to put them in the comment section, or any suggestions over how I can improve or something like that. Feel free to put them in the comment section. Thank you.
Hello and welcome, guys. This is Chahel here, and today I'll be explaining the tutorial for problem C, matching palindromes in Kickstart Round E. As you could see, I was able to solve problems A, B, and C, and now I'll try to explain problem E to you in case you had any difficulties in it. So, the task of problem E is in a sense that we have been given a palindrome P. So this string that we have been given as an input, it's already a palindrome. And what we need to do is that we need to find another string Q, which if we concatenate with P, so we'll get a string PQ. This string is also a palindrome, the string PQ. And the important thing here to note is that string Q is also a palindrome. So basically a palindrome plus palindrome equal to a third palindrome. This is what we need to do. So that's in general like test cases and constraints on n and all. So if you see there are 100 test cases, and in the first test set n is as big as 10 power 3, and in the second test set n is as big as 10 power 5. So this means that in the first test set a solution that is O of n square would pass. However, in like the second test set you need a solution that is O of n to complete it. Now so we'll just like try to solve the example test cases. So if you see, the first test case is ABA, and we need to find a palindrome that when added to this will also be a palindrome. So one thing we can note is that the whole string is a palindrome, like after addition also. So uh, the string Q, it should have these elements written this way if we traverse through it, and Q is non-empty obviously. So it will be something like, so just to like try out, we'll first write just A. So as you can see, A is a palindrome, but this whole string A B B A A won't be a palindrome. So we write BA isn't a palindrome, so that doesn't work out. If we write BBA, this makes the whole string palindrome, but BBA in itself isn't a palindrome. So now we just add A. So as you can see, ABBA both are palindromes, and together they form a palindrome. So one trivial thing that we can note from here is that if nothing works out, we can just take the whole string P and place it again, and that will form PQ, and that satisfies our condition. But we need to see if we can do better. So let's see in the second test case. So now in this, like we need to go this way. So first we'll just take C, and as you can see, C is a palindrome, and this whole string will also be a palindrome. So C is the correct answer here. Now if we go on to the third test case, so while traversing from here, we'll first write C. C is a palindrome, but this whole string PQ won't be a palindrome. Then we write D. DC isn't a palindrome, so that won't work out. And then we write C. So CDC is a palindrome, And if we see the whole string, that also forms a palindrome. So this works out as our solution for the third test case. So in essence, what we basically need is for this string to a palindrome. But from what we have seen is that this string is say some substring of p from sub range to some range. So in a sense, like if we have any p which is like a big string, so we'll just traverse it a bit and find an endpoint. So this thing, we'll call it q. It's like basically this endpoint might come at end also, it might be the first character also. So this whole thing will be our string q, and we'll append this to p here. Now the thing is q should be a palindrome. So we need to check whether this string is a palindrome. And after doing that, what we basically need is that this whole string to be a palindrome. So if you see the whole string, these two sections will match with each other. So what we need is the part of p which is not in q should also be a palindrome, this part. So in a sense, if you see, what we are doing in this question is that we are taking the string p, and we are dividing it into two substrings, and this part shall be q, and what we need is for the both of the parts to be palindrome. Now so basically what we'll do is, we'll iterate, like a naive solution to this would be that we take an iterator from like 1 to n, and this what this iterator will do is like it will check whether the right string and the left strings are palindromes. Now if we see, so the each for each iteration we'll need O of n time, because we'll need to check both sides of the string to be palindromes, and there will be total of n iterations because the iterator will go from 1 to n. So this will be the trivial O of n square solution if we see. Now but the thing is, this will only pass your first test set, and won't pass the second test set. However, like if you want to see how I've implemented for the first test set, we can see that here. So firstly, like see, in the first attempt basically I had done this mistake that uh, I assumed that the string q need not be palindrome. I missed out that information, and so I failed that time. In the second attempt, yeah, in the second attempt basically, what I did is, so as you can see, this is our iterator which is going from 1 to n, and for every value it is checking if q, basically the substring of p, is a palindrome. If it is a palindrome, and if the remaining string which uh, is also a palindrome, then we are outputting q. Now this is obviously a n square solution, and hence it's only passing the first test set and failing on the second test set. Now to solve this in O of n square, O of n basically, if you want an O of n solution. So one thing to notice that there's also O of n root n solution, which is kind of brute force. Like you just kind of you come to know that basically one string should be there, and that string should repeat throughout the string p, and you check that for various strings, and that will take you O of n root n. So that's the brute force solution, and it passes. But the O of n solution is the most optimal one, and this is based on Macken's algorithm. So what we basically do is, we create an array corresponding to a string. So what this array will store is that, like the ith element of this array would store that about s, about this element p of I, what is the longest palindrome that we can have, the length of the longest palindrome, that will be stored in a. P of I should be the center of that palindrome. So basically what we, so this is the basic idea of how we, so now we need to go on to the idea of how we'll calculate this array. So if you want, you can pause the video here and try it out for yourself, otherwise we'll continue on. So one interesting observation is that we'll one interesting thing is that we'll maintain two pointers L and R. So these two will be the endpoints of the last palindrome encountered, which are the furthest endpoint. So basically, R shall be maximum in that palindrome. So that way, what we'll basically do is like, see, say you reach some point where like you have a palindrome of, let's say, length. You have a big palindrome about one of the points, like say some point J, and this palindrome has endpoints L and R. Now you reach some element I ahead of it. So for this I, basically, if you want the value of this function a of I, what we'll do is we'll take its mirror image about J, which is basically this element, which is L plus R minus I, and we'll try to see the value of A here at A of L plus R minus I. So now if this value is less than R minus I, which is this length, then obviously the longest palindrome about I wouldn't exceed R minus I, and it shall have this value only, and we'll provide this value here. Now say, just in case this value is greater than R minus I, that means that the palindrome about this point goes beyond our initial palindrome, and so in this case we'll just keep the value of, we'll use our primitive function that is basically comparing the elements from R minus I to whatever element, whatever maximum element we can go to, and we shall do that about I. And in the other these, this is the case when I is inside your uh, longest substring, which is palindrome. Say I is outside the substring, then we'll again use the naive approach of comparing elements on either side and finding the largest subarray. And once this subarray has been calculated, we'll update R once again, and we'll continue doing this. So in essence, we'll have the value of A of I about each point. Now, once we have that, what we'll basically do is we need to divide our whole string into two parts. So we'll run a pointer I till n by 2, and we'll check if the value of A of I is equal to I plus 1. So that way, that will ensure that this string is palindrome, and if this is true, then we'll check whether this is a palindrome by checking the value of A of this element. And if both are true, then basically this string will become our queue, and we'll output it. And say we reach to n by 2 and we find no such string, so in that case we'll just output the whole string. So that way our algorithm will run. And just a technicality that we'll have to note in this is that our algorithm is calculating palindrome centered about an element. Now the issue with this is that, let's say we take something like say this element, yeah. So in this this string is a palindrome deed. My net is cupping a bit, but yeah. So say we have a string something like deed. So deed written twice. So in that case, basically, what we'll have is that we'll take the first. Yeah, so the technicality is that, say we have a even length palindrome, so the palindrome is even length. So in that case, it won't be centered about an element, rather it will be centered in between two elements. And this won't come in our array by the technique we have done. And so to ensure that we are able to get such arrays also, like for this example basically, so we won't get this. So to get that also, we'll just do one step, is that for the string what we'll do is we'll add hashes everywhere. So between each element, we'll add hashes. And after adding all the hashes and so on till the end, uh, after doing this, we'll uh, change our parameters of I and n accordingly, so that we can check up with that it can be divided into two parts, which are palindromes. Basically, these hashes won't affect the letters that come in the palindrome, but it will just help us find out, say, the even length palindromes as well. And this is basically mankind's algorithm. Now, to see why this runs in O of n, you can note that the pointer r, it runs, so if anytime your r doesn't change, so that time, like whenever you're going to a new I, there are two cases. Your I is inside, and there are three cases. Basically, I is inside the old palindrome, and it has a length smaller. In in such cases, what we are basically doing is we are doing an O of 1 operation. So that takes constant time. Say your I is bigger than this, then we are increasing R each time, and the number of operations done in that will be roughly equal to the increase in R. And similarly, if I is outside, then also we are increasing R, and in that case also the number of operations done will be roughly the increase in R. And in all, we know that R starts from 1 and it goes till n. So that way we know that R increases only n times. So the number of operations shall be O of n. And this is basically the clever solution of Mankan. And you can see my implementation here. So yeah. So first what I've done is I've taken the string as input here, p. Then I have created a function nstr. So this function basically adds those hashes in between the string. So I pass the string into this and store it another string. So that way I've got the new string x. Now once I've got x, uh, I create a vector a, which is vector or array basically, which is the values of the longest palindrome about each element of x. So this is the function that will run that Mankind's algorithm basically. So as you can see, I've covered the various cases of whether it fits in or not, I fits in or not, or it's bigger and all. And here, if you see, LNR get updated every time. So this algorithm will basically calculate that array for me, and then after calculating the particular array, I'll just check whether the string q is a palindrome, the sub array till we cut till I, and then I'm checking if the other half is also palindrome in this line, and if that is the case, then I'm breaking the loop and I'm outputting the string q. And this is basically the O of n solution for this problem. I hope you like the tutorial. If you have any suggestions or questions, feel free to type in the comment box. Me and Anmol will try our best to get to any of your queries. Thank you.